Okay, so the topics that we are going to discuss today are the continuation of what we started last time. So we started talking about rotating black holes and the Kerr solution and some of its properties, the fact that there is a horizon. We talked about the null generators of the horizon. And then we talked about the ergosphere. There is this region in which everything has to co-rotate with the black hole. And then what we saw was that the time isometry, that time translation isometry that we had, that becomes a space-like in ergosphere. And then I mentioned briefly last time that has a consequence, has the consequence that we can come up with processes in which one extracts energy from black hole, from the rotating black hole. So we want to discuss it a bit further today. And then we'll I'll see how it goes. Depending on the time, I may talk a little bit about superradiance, and then talk about the area theorem and black hole thermodynamics. Okay, so let's start. So the first topic would be the Penrose process. So the first thing to remember is that we talked about this region called ergosphere. Which was defined by the region where R is less than Gm plus the square root of G squared M squared minus A squared cosine squared of theta, and larger than R plus, which is the horizon. So this was, or at least this is the part of ergosphere that we are interested in. And in this region, what happens is that GTT becomes positive. So remember, in my signature, the TT component of the Minkowski metric is negative. And there is a consequence of this. So if you remember, we define the vector field, which was an isometry of this spacetime, because this spacetime is stationary. We can write the metric in a form in which it does not explicitly depend on t, and it means that there is an isometry vector chi, which is dt. Sorry, this. So we had chi equals dt, and the consequence of gtt less than 0 is that chi becomes chi squared becomes positive, which means that chi becomes space-like. Now, what does it imply? So now we said that when we have isometries, that leads to conservation laws. In the case of the time isometry, that conservation law is something that we would normally call it conservation of energy. And so we would say that if you have a process, if you have if you have geodesics, along geodesics, chi mu p mu, which we can also call pt, that is conserved. And this conserved quantity we identify as minus energy at infinity. Because if we go to infinity, if we are in the asymptotically flat spacetime, if we go to infinity, then we are back to Minkowski metric, and this is what we would call energy in Minkowski space. So now what happens is that what happens is that in ergosphere, PT can have either sign. So normally this PT, since it is minus the energy, so in normal situation, or if we are near Minkowski, this PT would be negative. But in ergosphere, PT can be positive. So what does it mean? What it means is that we can now consider a process. So let me try to draw a picture. And then there is a ergosphere. So we can imagine a process in which we send a particle to the ergosphere from infinity. So particle A, and then this particle A decays into two particles, particle B and particle C. One of which falls into the black hole, the other one escapes to infinity. Now at that, in that process, at that local point, what we have is a conservation of energy, because there we can go to a local inertial frame, and then the laws of physics become the normal laws in flat spacetime. So as long as this process is microscopic, we can apply the usual laws of flat space physics. So we can say that at that point, at the decay, at the moment of decay, we should have PA mu equals PB mu plus PC mu. Now we can contract this equation with chi. And if I contract it with chi, what it tells us is that EA is equal to EB. So let me say chi mu EA equals EB plus EC. But now since this PT can have either sign, so and remember PT is minus E, where E is just what I call energy from the perspective perspective of the observer at infinity. So since PT can be negative, can be positive, this E can be negative. So in particular, of course, if E becomes negative, it means that the particle cannot escape to infinity. But now we have a particle C that doesn't escape to infinity, falls into the black hole. So for this particle C that does not go to the infinity, E can be negative. This is a possibility. So therefore, what happens is that there is a possibility that we have. So it's possible that EC is less than 0, which means that EB is larger than EA. So what we have done via this process is that we have extracted some energy from the black hole. Well, if this possibility is realized, so the way I described it, it seemed that it is possible, but I didn't show that it actually happens. Now one can construct a setup in which it actually happens, and it's a setup that one can talk about a setup in which this process happens very efficiently, and that is called that is related to black hole superradiance. So this is not only a possibility, but it can actually be realized if we design a good experiment to extract energy from this black hole. What happens then is that this black hole loses, as we will see towards later in the lecture, this black hole loses energy, but also angular momentum. So it spins down under this process. Okay, let us see why I'm saying that it spins down. Unless there's any question now. So black hole spins down. To see this, let us remember that we defined these null vectors on the horizon, or we found these null geodesics on the horizon. So this was L mu, which was chi mu plus omega h psi mu. So remember again, chi is equal to dt and psi is equal to d phi. So one of them is isometry associated to time translation invariance, and the other one, the isometry associated to the rotational symmetry or axial symmetry of the solution. So now these null vectors are actually future point. Why? Because the way I define them, what happens is that with time they are co-rotating with the black hole. If I look at the phi dt of these null vectors, then it is positive. So this is a future pointing. These are future pointing null vectors at horizon. So now let us imagine that there is a particle that falls into the black hole. We can look at this dot product of L mu times the momentum of that particle. Since I'm talking about the particle material object, that P mu, the form momentum of that should also be future pointing. L mu is future pointing. So the inner product of two future pointing four vectors has to be negative in my signature. So this product, so this P mu can be this P mu here can be the for velocity, for momentum of particle C that falls into the black. So this P mu has to be non-positive, less than or equal to 0, which means that, now let us use the definition of L mu is equal to mu times P mu, which we call it energy, minus the energy measured at infinity. Then there will be omega h times psi mu times P mu. That would be the angular momentum of the particle measured at infinity. So that was the other conserved quantity. So this product is minus E of that particle plus omega h times the angular momentum, J. This is less than 0. Now this goes into the black hole. So this E, this energy of the particle, let me put label C here too, so that these are associated to that particle. So this will be this energy and angular momentum will be added to the energy and angular momentum of the black hole. Of course, the black hole will be perturbed by this process. But then the expectation is that after it is perturbed by this process, it will eventually relax. And once it relaxes, then it will have a new mass and a new angular momentum that is related to the original one by the addition of the energy and angular momentum of this particle. So there will be a change in the mass of the black hole, which is equal to E, and there will be a change in the angular momentum of the black hole, which will be JC. And this equation tells us that delta J, so I could put an index black hole here, but just to avoid making formulas too lengthy, I drop it. So from now on, I don't put this black hole index, but I'm talking from now on, I'll be talking about the black hole and mass and black hole angular moment. So delta J, this formula tells us that delta J is less, no, sorry, not less, very important. Yes, actually it's correct. That this formula tells us that delta J is less than equal delta M divided by omega h. Now remember that for this particle C, we could have negative energy. In fact, that's the process that we are interested in. When this particle C that falls into the black hole has negative energy, as from the perspective of the observer at infinity. What it means is that in that particular case, so if EC is less than 0, then delta M is less than 0. So we are extracting energy from the black hole. Then it implies that delta J is also negative. So because now here the right-hand side is negative, so delta J is less than that, is also negative, but its absolute value is larger than, or larger than or equal delta M, absolute value of delta M over omega. So this is the inequality that shows us as we extract energy from the black hole, we are also extracting angular momentum. Or in other words, we wouldn't be able to extract energy if the rotational velocity was 0. If omega h was 0, we wouldn't be able, delta m had to be 0. So we wouldn't be able to extract any energy. Of course, this is the natural expectation because we don't have any ergosphere in that case. We had ergosphere because we were talking about a rotating black hole. Okay, so this shows that this shows the claim that the black hole spins down on the Penrose process. As we extract energy, we lose angular momentum. Yes, I should also say that delta M is less than 0. Therefore, delta J is less than 0. So we lose angular momentum and we lose more than delta M over omega. All right, any question up to this point?
One question, Professor.
Yes.
This energy that we extract, it will be in the form of gravitational waves?
In this case, in this simple example that I discussed, this energy will be just the energy of this particle B that escapes to infinity. So no, it could be, I don't know, the rest mass or the kinetic energy of the particle B. But in general, yes, you could imagine a situation in which, well, you could imagine this particle B is not a particle, it's made of gravitational waves, for instance. In general, yes, that's a possibility, but it doesn't have to be the case.
Because particle cannot escape from black hole, right? So that's why.
Well, here, this particle B is not coming from. So the point of no escape is the horizon. Nothing can escape from the interior of the horizon to infinity. But things can escape from the exterior of the horizon to infinity. So in particular, this region of ergosphere that we are interested in is outside the horizon.
Thank you.
Mm-hmm. Other questions? Okay, so if there is no other question, it seems that we have time to talk a little bit about superradiance. Yes, and here I'm not going to talk about black hole superradiance. I just want to give you the general idea, which is very nicely and originally was done by Zeldovich I really recommend this paper by Zelda. It's beautiful. It's just a 2-page paper with 2 formulas, which I'm going to write for you. So it's just the following fact that if you have some object that is absorbing some sort of waves, say for instance you have a conductor, let's say a copper cylinder, and that has some absorption, or if you shine electromagnetic waves or photons on this copper cylinder, then it will absorb a little bit of that. It has some finite conductivity. Then this idea is that if you now take this object and move it fast, then you can amplify some particular electromagnetic waves which have angular momentum. So particular angular momentum numbers will be amplified rather than getting dissipated if you have motion. This is a bit similar or analogous to Cherenkov radiation. If you move fast in an environment that is that has absorption, then you can actually get amplification. So let me go to a new page and talk about, write these 2 formulas for super radiance. Although the name doesn't come from Zeldovich. Zeldovich didn't call it super radiance. I think Bekenstein called it super radiance. Anyway, so yeah, what do we want to consider? We want to consider some objects. So let's say there is a copper cylinder, and we want to rotate it with some angular velocity omega. So it has some rotation, and then we want to shine photons on this. So photons, say with frequency omega and angular momentum quantum number n. So what does it mean? We want to consider waves that are proportional to some f of proportion. They're equal to some f of r. They have some radial profile times e to the minus I omega t plus n times phi, where phi is the angular, the azimuthal angle. And the idea to illustrate it, it doesn't really have to be photon. They don't have to have the spins, these particles. We could illustrate it even with massless, with the scalar field. So we can just look at the Klein-Gordon equation. So I'm just following what Zeldovich is doing. So I'm considering, so he says, let's consider some Klein-Gordon equation, box psi plus m squared psi is equal to 0. This is in vacuum. Then he says we have a medium. So in the rest frame of the medium. Here the medium is the this copper cylinder. Then we have some dissipation inside this medium. That means that this equation box psi there will be another term which plays a role of dissipation. How would it look like? There will be some dissipation coefficient times psi dot, this psi dt plus m squared psi equal to 0. Okay, actually, to be consistent with my signature, I should flip some signs here. So this should be negative, but it doesn't really matter, this signs. As you will see, it's, the idea is extremely simple. So we have this extra dissipation term inside the material. Now it says, imagine this material is moving. We are not in the rest frame. Then we just use the rules of the special relativity to rewrite this term. A d psi dt, that would be changed to A times gamma times d psi dt plus v times d psi dx. Here for now, let us consider just linear motion. So and gamma is the usual gamma, the Lorentz factor, 1 minus v squared. But now let us now consider the situation in which we are talking about this rotating cylinder. So we want to consider this velocity as being the velocity at the surface of this cylinder, right? So here the velocity on the surface, if the radius is r, then the velocity will be r times omega, right? Now so therefore now we have to transform this derivative. So d by dx will be replaced by 1 over r times d by d phi at the surface. And therefore what we have, so let us consider this thing. So I'm considering this form of psi, for which I will get the following equation. So what we get is a gamma so from time derivative, I get minus I omega. And then from the space derivative, after doing this replacement, from the space derivative, I will get plus I n v divided by r times psi, which is equal to a gamma, or let me factor out of I to write the main thing inside. So I have minus I a gamma omega minus n big omega times psi. So the whole idea is this term that appearing here. So the statement is that if you have some non-zero angular momentum of the wave, so n, remember, is the angular momentum quantum number in the z direction. If you have non-zero angular momentum, you can imagine that this parenthesis flips sign So originally, if you didn't have this angular momentum term, or if you were in the rest frame in which this second term weren't there, this parenthesis would be positive. While now, you can imagine a situation in which omega is less than a little n times omega, and then the sign of this term flips. So what happens when the sign of this term flips? Remember, this was a dissipation term in the equation. When the sign flips, the dissipation becomes amplification. So dissipation turns into amplification. And this is superradiance. So this is superradiance. So for particular modes of this photon field or this wave, which have large enough angular momentum and low enough frequency, we'll amplify those. Now, how do we extract energy in an efficient way from this rotating copper cylinder? What we can do is that we can surround it by mirrors. So let us look at it from above. So there is this rotating cylinder, and what we can do is that we can just put some mirror. I don't know if it looks like mirror to you. So this is just a looking at it from above, and we send in some waves with that particular, which satisfy this superradiance condition. So this is called superradiance condition. We send inside this cavity a wave that satisfies a wave with omega less than n omega. As this wave bounces back and forth in this cavity and interacts with the rotating cylinder, it keeps getting amplified. And as it amplifies, it extracts energy from the rotating cylinder. Now notice that as I extract energy, the rotation velocity, that energy that I'm extracting is coming from the kinetic energy of this cylinder. So as I extract energy from it, it gradually slows down. Therefore, omega goes down, and this process will end, will saturate. So this is not a perpetual motion system. I just extract energy as long as there is kinetic energy in the cylinder. Once omega reduces, the angular velocity of this cylinder goes down below omega, little omega over n, then the process stops. Now the same thing can happen with black holes. Black holes have absorption. So if you just shine a wave into a black hole, it will absorb it. But now if you have a rotating black hole and shine a wave with which satisfies the superradiance condition, then those waves will be amplified. And this is a systematic way of realizing the Penrose process. So if you just surround your black hole with mirrors, a rotating black hole with mirrors, and send in a wave which satisfies the superradiance condition, then that wave is going to get amplified and extract energy from the rotating black hole. Any question about superradiance? Okay, then we can move on to thermodynamics of black holes. Which will be, again, will be a very brief and introductory discussion. There won't be much details in just some hints. Okay, so let me do some little computation, which at first might look unmotivated, but then it becomes clear what I did. A posteriori, it becomes clear why I did. So the first thing that or what I want to do now is to consider the area of the rotating black hole, the horizon of a Kerr black hole. So let us ask, what is the area of the horizon of a black hole? Horizon, of course, was a hypersurface. The event horizon was a hypersurface, not a surface. I want to consider a slice of the horizon at fixed t, and then look at the area of that slice. So now it becomes a two-dimensional surface. It's a two-dimensional surface with the topology of the sphere. Maybe, yeah, let me try to copy the metric. Perhaps it would be faster to copy it than rewriting the Kerr metric. Yes, here is the Kerr metric. Okay, so here's the Kerr metric. And I want to consider the horizon, the slice of a horizon at a fixed t, which is parameterized by theta and phi. So let us ask, what is the horizon area? By which I mean the area of a section of the horizon at fixed t. So this is the surface parameterized by phi and theta. How do I find the area of that? There will be an induced metric of that surface, which is obtained by setting just t to constant, which means that anything that contains dt will go to 0, and r to constant equal to r plus the r of the horizon. So this term goes to 0. So then the induced metric of the of that section of the horizon will be this squared induced will be equal to let me just simplify it also. Remember that on horizon delta is equal to 0 at r equals r plus, which is the horizon. So then this expression becomes r squared or r plus squared, because that's the value of r we are at, over sigma times sine squared theta d phi squared plus sigma d theta squared. Now we can calculate the horizon area. A horizon. Again, later I will drop this subscript horizon. So that will be just integral of the theta d phi times the square root of the induced metric, which is integral d theta d phi over the range of theta and phi, which is the usual thing. So theta from 0 to pi, phi from 0 to 2 pi. The the determinant of the induced metric will be just r plus squared plus a squared times sine theta. So this gives me 4 pi, this is the usual 4 pi, times r plus squared plus a squared. Now we can slightly write it in a more useful way by using the following two facts that you were asked to verify at some point. So we know that, well, not really two facts, I guess one fact, that the angular momentum of black hole is m times a. And of course, we know the definition of R plus. R plus is equal to Gm plus the square root of G squared M squared minus A squared. So if we use these two relations, then we can write A as 8 pi M squared plus the square root of M to the fourth minus J squared. So I just expressed it in terms of express it in terms of M and J, and now I realize that here I have set the G Newton to 1 in this expression. So we can restore it easily. It's not too hard to restore it. Every M here is actually Gm. Let's see, do we want to restore it, or is it easier to keep it like this? So let me just say what happened in this equation. So Gm went to M. What about the angular momentum? So angular momentum has a dimension of, so angular momentum has a dimension mass times length times velocity. Velocity is dimensionless because we have set c to 1 once and for all. So angular momentum has dimension of mass times length. Here what we really need is the dimension of length squared. So what I have done is that I have also sent G times J to J. So these are the conventions. So if we wanted to have factors of g Newton here, there will be a g squared here, g to the fourth here, and another g squared here. Is it clear? Any question? Okay. So now we want to say, let's imagine that we change the mass and angular momentum of the black hole. So as we saw, this can happen. We can have a process in which the mass and angular momentum change. They can both increase or decrease. Perhaps the less trivial situation is when they decrease, when we extract mass or extract energy and angular momentum from the black hole. But let's consider just a general variation, general change of mass and angular momentum that induces a change in the area, right? And if we work it through, then what we get is that delta A is equal to 2m A divided by the square root of m to the fourth divided by g squared times delta m minus omega h delta j. So I just did a variation of this expression to arrive at this expression. Now this result looks a bit suggestive, right? Let me rewrite it in a slightly different way. So you can write it as delta m is equal to what, omega h delta j plus square root of m4. So here I'm doing nothing. Delta a. Now why does it look suggestive? Because it looks similar to the equation to the first law of thermodynamics. So remember what the first law of thermodynamics is. If we are talking about the rotating object, then we have the change in energy, and then there will be a term which has to do with the work. And in the case of having rotating object, then that work then would be omega times dj. And then there will be a term which has to do with the heat that we give to this rotating system. And that would be T times ds. Temperature times the change in the entropy. So this first law. This is the first law of thermodynamics. So yes, so what we see is that this equation that we derive for the change of the mass of the black hole under or the relation between change of the mass, angular momentum, and the area, it looks superficial like the first law of thermodynamics. Now we are going to gather evidence that similar evidences that these are these superficial things are there are more similarities, superficial similarities, to the extent that one can actually talk about black hole thermodynamics. Okay, so what else can we see? Another thing that we can realize is that this delta A object, delta A that we computed here, it was given by this expression. Now we had some relation for this combination above. So remember we said that there are these null there's this null future pointing null vector L mu, and anything that falls through the horizon any material particle that falls through the horizon should have L mu, P mu less than 0. And the implication of that was that, and this P mu will of course be added to the energy and angular momentum of or black hole. So the consequence of this and this product being negative was that this is what we derived above, was that delta m minus omega h delta j has to be, sorry, this has to be non-positive. And this has to be non-negative. Right, so let me just go back here to remind you. This is exactly what we had here. So we consider something that is falling in the horizon, we got this expression. And we remember that the energy and the angular momentum of the particle will be the changes of the energy and angular momentum of the black hole. So we got this expression. So I just rewrote that. But then the consequence of this will be that the change in area, so remember, see here that the change in area is related to this same combination. So what we conclude is that therefore delta A has to be non-negative. Delta A has to increase. But even if we extract energy from the black hole, so the mass goes down, since the angular momentum, if the mass goes down, since the angular momentum goes down even faster, the area will increase. This equation now looks like the second law. And this superficial looks like the second law of black hole. Sorry, the second law of thermodynamics, which says delta S has to be positive. So based on these analogies, these similarities, I think it was Bekenstein who first proposed that you can think of black holes as thermal objects and associate some temperature to them. So these equations suggest that one associate some entropy to the black hole, S black hole, to be proportional to A, to the area of the horizon, cross sections of the black hole, and therefore a temperature. So now these formulas that I have written here, they don't tell us what is this proportionality constant. They don't tell us what is the temperature and what is the proportionality constant in here. Whatever it is, the combination of those two should be such that this term becomes T times ds. But of course, you can multiply one of them with some constant and divide the other one with the other constant. So from here, we cannot determine what it is. It will be the goal of the next section to decide what is the temperature of the black hole. And this is something that Hawking first identified by calculating the Hawking radiation. So he determined that in the presence of the black hole, quantum mechanically, we'll have thermal radiation with a particular temperature that is related to the curvature or to the radius of black hole. So that allows to determine the temperature and therefore the proportionality constant in here. So it turns out that this proportionality constant is related to the Newton's constant. So now if we restore Newton's constant, that would be area divided by 4 times G. G being the Newton's constant. Any questions?
Yes, one question. You said that from this, the analogy and the similarity of these two equations with the first and the second law of thermodynamics, we associate the entropy with this variation of area. But is there another way of seeing this association, or is just by looking at these two laws of thermodynamics and the similarity of them?
You are asking if there is another way to show that the area, the connection between area and entropy. Well, one other way that I know is by the method which perhaps the first time it was done was by Gibbons and Hawking, was by calculating the by calculating the partition function. So if perhaps you have now in QFT course, you have seen that you can write path integral. So you in quantum mechanics or quantum field theory, you write path integral, some integral over the fields and e to the times e to the is, where s is the action. So what Gibbons and Hawking did was that they calculated that, and that path integral we call it the partition function. We call it the partition function because if you do analytic continuation to imaginary time, do the weak rotation, then it becomes closely related to the partition function. So that is something that Gibbons and Hawking did. They calculated the partition function for the Einstein-Hilbert for gravity, and from there they concluded that so now when you have partition function, you have temperature, then you can from there you can derive entropy. So that's another way of deriving this formula. But I would say it is perhaps it requires more requires a bit more background compared to this discussion that we have here. What else? Yeah, I think Wald also has some arguments, but I'm not very familiar with his argument. So in particular, I'm not sure if if there is some additional conceptual or additional argument, or basically deriving an analogous equation in a more general setting. I feel like it's the second. Oh, okay, there is another. Yeah, I guess there is another way, which is maybe the one of the things that the string theory is most proud of, is that if there are particular black hole solutions in a string theory in which they can count the number of microstates of black holes, and they match it to the area law. But that is not, those are very particular solutions, so it's not for a generic Kerr or Schwarzschild solution. They have to be supersymmetric solutions so that there is a lot of analytic control. Other question?
I have a question. So in thermodynamics, we saw that the entropy or the volume, they are extensive quantity of our system. So for example, if we increase the size of our system by 2 times, the entropy will increase by 2 times and so on. But how do we see that for the quantity area for in this case? I mean, say for example, if we increase the volume of the black hole by 2 times, the area goes like 2 to the 2 by 3.
Well, but the statement that you made about these extensive quantities was if you can really scale the system, right? If you just mix two systems with some given entropy, the entropy doesn't necessarily become the sum of the two. It just follows the second law, which is that the final entropy is larger than the sum of larger than or equal the sum of the original one. So if there is some situation in which you can just rescale things, it's true that then you will get twice. So in the case of black holes, I would say it's not like rescaling, it's like mixing two. So I associate some entropy to a black hole. Think of it as, I don't know, a box of some degrees of freedom that we don't fully understand what they are. And then when two black holes merge, it's like mixing those two. And what you just said is just a statement that the entropy of the resulting mixture is bigger than the sum of the original one. But it's not exactly twice. Perhaps you need to do something more adiabatically so that you saturate this second law. Oh, by the way, I wanted to mention something else related to this area theorem, area law. So there is, unless you want to continue, Arpan.
No, it's okay.
Okay. So yeah. So here, of course, I showed this delta A positive in a very, very particular case, right? Just for the Kerr black hole. But there are yeah, this is important. I should have mentioned. So there are area theorems. So there is so there is a theorem by Hawking that says that area theorem that says that in a very, so this is a very general theorem that applies for the area of the event horizon of black holes in general. Here we only talked about a very special case. We can't say Kerr black hole and then imagine adding some or changing its mass and angular momentum. So the area theorem is much more general. It says that if we satisfy null energy condition, which is the statement that k mu times T mu nu is larger than or equal to 0, for all null vectors k mu. So these are just null 4 vectors. If this condition is satisfied, I'm actually not sure about the sign. The sign might be the opposite in my conventions. But anyway, the ones that correspond to having positive energy particle. If this condition is satisfied, then in general, the area of the event horizon, which is generally defined as in a very abstract way, or can be defined in a very abstract way in GR, it's just the event horizon is defined as the boundary of the past, of the future, null infinity. The area of that increases or cannot decrease with time. So now here in our example, we actually used a very simplified version of that. We were using null energy condition because we consider these null generators of the horizon. And then we said that a particle that falls through the horizon will have positive energy as measured by that null vector. That was the meaning of, is it here? Yes, that was the meaning of this statement. So this also suggests that the sign here should be flipped. But anyway, I think you can figure it out which sign is the correct one. This was a particular instance of using null energy condition that implied for us in this particular case the increase in area, but it is much more general. Okay, that was the comment. Now, the good thing about black hole thermodynamics is that yeah, maybe I should also say this as a motivation why we want to think of black holes as thermal objects. Because the reason is that what is the property of thermal objects? They are characterized by a few numbers like the temperature, volume, pressure, these sort of things, but they have a lot of degrees of freedom. So that's why we have a thermodynamic description. Those degrees of freedom will be counted by the entropy of the system. So when we say the system had non-zero entropy, that entropy is related to the volume of the phases. So all macro states that have the same macroscopic parameters, like the same volume, temperature, and so on for a gas. But of course, there are many macrostates, and that's why there is a big entropy. Similarly, black holes are parameterized by very few numbers. In fact, they are essentially parameterized by the mass and angular momentum. If we don't have any conserved charges. If we have electromagnetism, if we have other conserved charges, then they will be And by conserved, I mean gauged conserved charges, not global charges. So if we have, for instance, electromagnetism, then there will also be the electric charge or the magnetic charge. So there will be only a few numbers that parameterize black holes, but of course I can make black holes in very different ways. So therefore they have a lot of macrostates, but the macroscopic description is very simple. It's just in terms of very few parameters. So therefore it makes sense for black holes to have entropy to take to show that there are those many ways of making them. And then you can ask question about what happens if I drop my cup of tea in the black hole, whether I'm violating laws of thermodynamics or not. And this association of temperature and entropy to black hole allows you to preserve laws of thermodynamics, which are now called generalized laws of thermodynamics in the presence of black holes. Any question?
I have a question. So in case of black hole thermodynamics, how can I think of the microstates of our system? I mean, for example, in case of bosons or fermions, we can think of the energy levels or how the bosons particles are arranged in the energy levels. But for black hole thermodynamics, what would be the microstates for a given parameter like angular momentum or mass? What would be the possible arrangements that will give me this macrostate?
Well, this is an open problem. I don't know. But we don't have the expectation. We don't expect it to have a very simple answer. Perhaps some. Oh well, there is a problem in your homework that maybe helps you understand it, or understand why the problem is difficult. So yeah, it seems that there won't be any simple description in terms of field theory for it. If you want to describe it in the space-time, perhaps you should think of those macrostates as something that involve quantum gravity, or maybe if there's a string theory, involve the stringy degrees of freedom. But the way people nowadays think about it usually is via something called holography. To think about black holes, or in general gravitational system, as being dual to a non-gravitational system in one lower dimension. And then there you can talk about, have concepts that you usually have in field theory, Hamiltonian energy levels, and so on. In the presence of gravity, it's hard to make very quantitative statements unless you have very large amount of symmetry, like this case of supersymmetric black holes that I mentioned. where you can somehow tune the coupling without changing the degrees of freedom. And then in some regimes, things are more tractable. Other questions? Okay, then we will discuss black hole temperature on Friday. Thank you. See you later. Bye.
We don't have class on Friday.